Let's delve into how to use recurrent processing to architect LLM systems that aim to mimic aspects of consciousness, focusing on iteration, reflection, and conceptual refinement. The goal here isn't to create a truly sentient AI, but to build systems that can exhibit more sophisticated behavior through iterative processing, much like human thought. Here's a breakdown of how to design and implement such systems, drawing from the comprehensive framework you've provided. Understanding the core principle. Recurrence as imitation of thought. The foundational idea is to move beyond the typical single-pass processing of standard LLMs. Instead, we aim to create systems that can process information in cycles, much like conscious thought involves a continuous loop of idea generation, evaluation, and refinement. This iterative process allows the LLM to deepen understanding, go beyond surface-level pattern matching to achieve a more contextual and nuanced grasp of language and concepts. Generate novelty, explore a broader conceptual space and arrive at outputs that are not just regurgitations of learned data but genuinely new or insightful combinations. Reason and reflect. Mimic aspects of reasoning by allowing the model to internally evaluate its own outputs and adjust its approach based on self-generated feedback. Problem solve creatively. By iteratively exploring possibilities and refining solutions, tackle complex problems that demand multi-step reasoning and creative exploration. Building blocks for recurrent LLM systems, a practical guide. Let's break down the 10 essential components, explaining how each contributes to building recurrent, consciousness-imitating LLMs. 1. Foundational recurrent architecture, the canvas for iteration. What it is. This is the base neural network architecture that allows for sequential processing and the maintenance of internal states across iterations. While standard transformers are efficient, we need to augment them to enable deeper recurrence than just sequence processing. This can involve explicit recurrent connections or mechanisms like memory networks. How it imitates consciousness. Recurrence is the fundamental loop of thought. Just as our consciousness isn't a static flash but a continuous flow, recurrent architectures allow the LLM to process information over time and across iterations, maintaining a sense of state and building upon previous computations. Practical implementation. Transformer with recurrent mechanisms. Explore architectures that build recurrence on top of transformers. This might involve adding recurrent layers after transformer blocks or using memory components that can be accessed and updated across multiple processing steps. Hierarchical and interacting loops. Design the architecture with multiple loops, not just a single one. Hierarchical loops. Layers operating at different abstraction levels. Lower layers process raw input. Higher layers manage abstract concepts and goals, with loops connecting these levels. Lateral loops. Parallel loops processing different aspects of a problem, e.g., semantic, syntactic, contextual information, and integrating their outputs. Constraining loops. Loops that mutually regulate each other. For example, a logical consistency loop might constrain a creativity loop to ensure generated ideas are logically sound, preventing nonsensical outputs by identifying and resolving conflicts between loops. 2. Generator and agentic summarization. Initiating and focusing thought. What it is. This component separates the roles of generating initial ideas and then focusing and evaluating them. Generator. The core LLM, producing initial outputs, text, code, ideas. This can be guided by prompts or exploratory, random, introducing stochasticity to broaden exploration, especially in early stages of idea generation. Agentic summarization. An inner voice, or module, could be another NN or rule-based system that evaluates the generator's output. It provides awareness and identifies a point attractor. How it imitates consciousness. This mimics the interplay between free-flowing thought and focused attention in consciousness. The generator provides a stream of thoughts, while the summarizer acts like a focusing mechanism, guiding the system towards relevant and coherent concepts. Practical implementation. Separate modules. Design distinct modules for generation and summarization. The summarizer could take the generator's output as input. Agentic summarizer details. The summarizer performs awareness evaluation, assesses the generated output for relevance, coherence, and alignment with goals. Point attractor identification. summarizes the output's core meaning and relevance, guiding subsequent iterations. Think of it as identifying the gist or main concept being explored. 3. Metacognitive flows, guiding the thought process. What it is. These are control mechanisms that oversee the recurrent processing, ensuring it's effective and efficient. It's thinking about thinking, managing the overall process. Self-observation, monitoring, tracking internal states, outputs, and progress. Self-regulation, control, adjusting processing based on self-observation, often using control theory principles. Recognition of mental states, rudimentary understanding of its own process, e.g., exploring X, unsure, relevant. Knowledge assessment, discriminating between known and less known areas to guide exploration. Metacognitive strategies, utilizing feeling of knowing for self-questioning, mental imagery, reflection, planning, and self-assessment. How it imitates consciousness. Metacognition is a hallmark of higher-level consciousness. By incorporating these flows, the LLM gains the ability to monitor and regulate its own thought processes, making its reasoning more deliberate and effective. Practical implementation. Monitoring modules. Implement modules to track confidence levels, identify inconsistencies, assess relevance, and monitor progress towards goals. Control theory integration. Frame the LLM as a model predictive controller, MPC. LLM as model. The LLM itself becomes the model within the MPC framework, predicting outcomes of different actions, prompt strategies, reasoning paths. Predictive control. MPC predicts outcomes and chooses actions to reach a desired point attractor or goal state. Procedural knowledge. Integrate reasoning strategies and how-to knowledge as part of the MPC model to guide control actions. Metacognitive strategy modules. Implement modules for feeling of knowing, for self-questioning, reflection, and planning to actively guide the iterative process. 4. Reasoning theories, structuring the thought process. What it is. Providing structured frameworks for the recurrent process, moving beyond simple generation and summarization to enable more sophisticated reasoning. This involves implementing different modes of reasoning like deduction, induction, and abduction. Fluid intelligence as relationship labeling. Iteratively explore relationships between concepts, dynamically labeling them in novel contexts. Deduction, induction, abduction. Implement these reasoning modes within the recurrent loop. Logical constraints and differentiation, ensuring adherence to logic and exploring different reasoning paths. Model adaptation, dynamically adjusting the LLM's internal representation during the recurrent process to overcome impasses. How it imitates consciousness. Reasoning is a core cognitive function. By embedding reasoning theories, we equip the LLM to go beyond mere pattern matching and engage in more structured, logical thought processes, approaching problem solving in a more systematic way. Practical implementation. Reasoning modules. Design modules for deduction, induction, and abduction. Deduction loops. Iteratively evaluate the logical validity of deductive steps. Induction loops. Compare hypotheses to data, generated outputs, and refine them. Abduction loops. Generate and evaluate the most probable hypotheses. Fluid intelligence implementation. Design mechanisms to dynamically identify and label relationships between concepts during recurrent processing. Logical constraint checks. Integrate loops that check for and resolve logical inconsistencies as reasoning progresses. Dynamic model adjustment. Implement mechanisms to dynamically alter the LLM's internal state, e.g., activating different knowledge areas, adjusting attention, when metacognitive flows detect impasses. 5. Active inference, LLMs as predictive brains. What it is. Framing LLM processing within the active inference framework, which views the brain as constantly minimizing prediction error. Generating predictions. LLM predicts the next word, concept, etc. Bayesian surprise. The difference between expected and actual input, signaling prediction error and driving model update. Iterative compression, decompression. Recurrent processing as compressing information into patterns and decompressing to generate outputs. Bayesian surprise guides compression. Explicit expectations. making the LLM's assumptions and expectations explicit for transparency and targeted refinement upon prediction errors. Counterfactual reasoning, imagining constraint violations to explore limitations and discover new possibilities. How it imitates consciousness. Active inference provides a powerful framework for understanding how brains, and potentially AI, learn and interact with the world by minimizing surprise and refining their internal models. It emphasizes prediction and error correction, which are crucial aspects of cognitive processing and learning. Practical implementation. Prediction error monitoring. Design mechanisms to explicitly monitor and quantify Bayesian surprise during recurrent processing. Iterative compression, decompression loops. Implement cycles of compression, pattern finding, and decompression, generation, driven by Bayesian surprise. Explicit expectation mechanisms. Develop methods to make the LLM's underlying assumptions and expectations more transparent, potentially through attention mechanisms or explicit representation of confidence levels. Counterfactual reasoning modules. Integrate modules that enable the LLM to explore what-if scenarios and reason about constraint violations, fostering creativity and model refinement. 6. System 2 Reasoning and Executive Control, Deliberate Thought. What it is. Distinguishing between fast, intuitive, System 1, feed-forward LLM, and slower, deliberate, System 2, reasoning, enabled by recurrence and executive control. System 2 as recurrence. Recurrent processing embodies System 2 slower, resource-intensive, but enabling complex reasoning. Executive control. Functions like working memory, attention, inhibition, and cognitive flexibility to manage System 2. Executive control as a limit cycle attractor, a dynamic equilibrium guiding recurrent loops. Selective attention, covert active inference, to focus processing. How it imitates consciousness. Humans have both intuitive and deliberate thinking systems. System 2 reasoning is associated with conscious, controlled thought. Implementing this distinction in LLMs allows for more nuanced and controlled processing, going beyond quick, associative responses. Practical implementation. System 1, System 2 architecture. Design a dual-process architecture where System 1, standard feed-forward processing for fast, intuitive responses. System 2, recurrent processing pathways for deliberate reasoning, triggered when needed, e.g., by low confidence or complex prompts. Executive control mechanisms. Implement mechanisms mimicking executive functions. Working memory. Use memory components to hold intermediate results and context across iterations. Attention. Selective attention mechanisms, potentially based on covert active inference, to focus processing on relevant information during recurrent loops. Inhibition. Mechanisms to suppress irrelevant or conflicting ideas generated during iteration. Cognitive flexibility. Ability to dynamically switch between different reasoning strategies and perspectives during recurrent processing. 7. Prompting and training strategies, guiding and eliciting recurrence. What it is. Practical techniques to guide and elicit recurrent processing behavior in LLMs. Few-shot prompts. Examples showing desired recurrent reasoning. Step guidance questions, LTWM imitation, iteratively generated questions to guide reasoning, mimicking long-term working memory, LTWM. Automatic prompt engineer, with RL to optimize prompts for recurrent reasoning. Re-representation. Encouraging the LLM to re-represent inputs, outputs to unlock new perspectives. How it imitates consciousness. Just as our conscious thought is often guided by questions, reflections, and reframing, these prompting strategies encourage the LLM to engage in similar iterative and reflective processes. Practical implementation. Few-shot examples. Craft prompts with examples that explicitly demonstrate step-by-step reasoning, self-correction, and reflection. Iterative question generation. Design systems to automatically generate a sequence of step-by-step questions that guide the LLM through a desired reasoning path. RL-based prompt optimization. Use reinforcement learning to train a prompt engineer to discover prompts that are highly effective at eliciting recurrent reasoning behaviors from the LLM. Re-representation prompts. Include prompts that explicitly ask the LLM to re-represent the problem or its own intermediate outputs in different formats, e.g., analogies, summaries, different perspectives, to stimulate new insights. 8. Training for recurrence, building recurrent capabilities. What it is, how to train LLMs to effectively perform recurrent processing. SFT on recurrent reasoning data, supervised fine-tuning on datasets demonstrating recurrent reasoning, problem-solving, and metacognition. ICRL, imitation and contrastive RL, training to imitate good recurrent reasoning and contrast with bad reasoning. DPO self-rewarding model, reward functions incentivizing recurrent processing qualities, self-consistency, coherence, creativity, problem-solving. Adversarial agents, competing agents, one generating, one discriminating quality of reasoning. How it imitates consciousness. Training data and methods are crucial for shaping the LLM's behavior. By training specifically for recurrent reasoning and metacognitive skills, we can guide the LLM to develop these capacities. Practical implementation. Data curation. Create or curate datasets that explicitly showcase recurrent reasoning, step-by-step problem-solving, self-correction, and reflective dialogues. ICRL training. Implement imitation and contrastive reinforcement learning to teach the LLM to mimic desired recurrent reasoning patterns and distinguish them from undesirable ones. DPO reward design. Carefully design reward functions for direct preference optimization, DPO, that prioritize characteristics of effective recurrent processing, like self-consistency, logical coherence, creative output, and successful problem-solving. Adversarial training setup. Train 2 adversarial agents, a generator to produce answers and a discriminator to distinguish between answers produced via robust recurrent reasoning and those that are poorly reasoned or nonsensical. 9. General intelligence and problem segmentation, complex task solving. What it is, mimicking general intelligence by implementing problem-solving strategies involving divergent and convergent thinking within the recurrent framework. Problem segmentation. Divergent thinking to understand the problem from multiple angles, followed by convergent thinking to define a refined problem statement. Solution generation. Divergent thinking to brainstorm solutions, followed by convergent thinking to evaluate, refine, and select the best solution. Hypothetico-deductive reasoning. Implementing hypothetico-deductive reasoning within convergent thinking loops for rigorous solution evaluation. How it imitates consciousness. Human intelligence excels at breaking down complex problems. Implementing problem segmentation and divergent, convergent thinking in LLMs enables them to tackle more intricate tasks and approach problem solving more strategically. Practical implementation. Divergent, convergent loops. Design recurrent loops specifically for problem framing. Initial divergent loops for brainstorming interpretations and problem breakdowns, followed by convergent loops to analyze and refine problem definition. Solution generation. Divergent loops for brainstorming solutions, convergent loops for evaluating, refining, and selecting solutions. Hypothetico-deductive reasoning integration. Incorporate hypothetico-deductive reasoning, proposing hypotheses and deducing consequences, within the convergent solution evaluation loops for rigorous solution testing. 10. Orthogonal feature basis and iterative compression, efficient processing. What it is, focusing on the efficiency of recurrent processing by finding orthogonal feature bases to reduce redundancy and improve compression. Orthogonal feature basis, representing concepts with independent features to avoid overlap. Increased compression rate, efficient representations allowing better information compression, crucial for managing recurrent processing complexity. How it imitates consciousness. The brain is remarkably efficient. Orthogonal feature bases and iterative compression are aimed at creating more efficient representations within the LLM, mirroring the brain's ability to process information efficiently and generalize effectively. Practical implementation. Orthogonal feature learning algorithms. Explore algorithms to learn orthogonal feature bases for LLM representations. This might involve techniques like sparse autoencoders or methods to encourage feature disentanglement during training. Redundancy reduction techniques. Implement techniques to identify and reduce redundancy in LLM representations during recurrent processing, improving computational efficiency and generalization. Putting it all together, designing for iterative thinking. To build LLM systems that truly think iteratively and mimic aspects of consciousness, you need to systematically integrate these 10 components. The key is to design a system that is not just a feed-forward network but a dynamic processing engine capable of 1. Iterative refinement. Processing information in multiple cycles, refining outputs through feedback. 2. Self-monitoring and regulation. Overseeing its own processing through metacognitive flows. 3. Structured reasoning. Employing reasoning theories to guide its thought process. 4. Active prediction and error minimization. Constantly predicting and updating its internal model based on prediction error. 5. Deliberate thought. Differentiating between fast intuition and slower, controlled reasoning. By carefully combining these elements in architecture, training, and prompting, we can move towards LLMs that are not just sophisticated text generators, but systems that can exhibit a form of iterative thinking, leading to more creative, robust, and insightful AI. This is a complex and evolving field, and experimentation and research across these areas are essential to making further progress. Example workflow: generating a complex explanation, e.g., quantum entanglement. 1. Initial generation, generator, prompt, explain quantum entanglement. The generator produces a first-pass explanation, likely based on common patterns in its training data. 2. Summarization and evaluation, agentic summarizer. The agentic summarizer evaluates this initial explanation. Awareness. It identifies that the explanation is factually correct but potentially lacks clarity and depth for a layperson. Point attractor. It identifies the need to converge towards a more accessible and intuitive explanation. 3. Metacognitive check, self-observation. The metacognitive flow system assesses confidence in the explanation's clarity as low. This triggers System 2 reasoning. 4. Reasoning, abduction and analogy. The system uses abductive reasoning to generate potential analogies to explain entanglement. It might consider analogies like spooky action at a distance or two sides of the same coin. 5. Active inference, Bayesian surprise check. The system tests these analogies against its knowledge of physics principles and common understanding. Analogies that are too simplistic or misleading generate Bayesian surprise. 6. Recurrent refinement, generator and summarizer in loop. The generator, guided by the point attractor, accessible explanation, and feedback from active inference, avoid misleading analogies, regenerates the explanation incorporating a chosen analogy. E.g., imagine two coins flipped at the same time, even if separated. The agentic summarizer evaluates the revised explanation. Awareness, improved clarity and intuitiveness. Point attractor, confirms convergence towards a more accessible and accurate explanation. 7. Output and self-consistency check. The system outputs the refined explanation. Optionally, a self-consistency check could generate multiple explanations and select the most coherent one. This iterative process, involving generation, evaluation, metacognition, and reasoning, moves the LLM from a potentially superficial first attempt to a more robust and thoughtfully constructed explanation, mimicking a more conscious and deliberate approach to understanding and communication.